We've seen how something we think of as having a wave nature, light, which is electromagnetic waves, can be thought of as having a particle nature as well. We can think about light as being made up of photons. So light is quantized in units of a particular size. That was our first piece of quantum physics. Light is quantized in units of photons. But early investigators said, well, if something we think of as being a wave has a particle nature, how about something we think of as having a particle nature, like an electron? Could it also have a wave nature? And the answer is yes. Electrons, protons, other particles have a wave nature associated with them. And this leads to some very, very interesting behavior. Think about this. If I ask you where this tennis ball is, you can say pretty precisely it's right here. It's got a definite position. But how about this? How about this? If I shake a wave on the wave machine and I ask you, where is the wave? Well, that's a trickier question. It's kind of spread out. You could say the position is the peak, but it's not really. The wave is a distributed phenomenon. And that was kind of a narrow wave, but I could make a wider wave. And where is this one? It's spread out quite a bit. So the question of where is something is a trickier thing for waves. And as a consequence, because particles have a wave nature, it's a trickier thing for particles. And so in quantum mechanics, we have this idea of uncertainty. And we learn the uncertainty principle in chapter 28. You can't know the position and the velocity of a particle to arbitrary accuracy. So take a look at this equation. What this equation means is this. The product of the uncertainty in the position times the uncertainty in the momentum is greater than or equal to some number. So think about this. If I was to take a particle and measure its position more precisely, I'm going to reduce the uncertainty in the position. What would happen to the uncertainty in the velocity? We'll give you some choices. And because particles have this wave nature, if you specify the position more accurately, you lose knowledge of the velocity. You lose the ability to be able to specify the velocity to the same degree of accuracy. So if you know where something is, you can't know where it's going. And that is a remarkable fact of quantum physics. But the wave nature of particles has a more important application. And let's look at this. I have a string which is stretched between two fixed points. And if I set up a wave on here, the wave has to exist between here and here. The wave exists within a constrained region of space. And when you make a wave exist within a constrained region of space, you can't get any arbitrary wave. I can only get certain possible standing wave modes. We've seen this before. So I can have this wave, but if I change the frequency, I don't get a resonance. The waves go away until I adjust the frequency to reach another standing wave mode, and now I get a wave again. So I can have that first wave, I can have this one, I can have this one, I can have certain possible standing wave modes, but I can't get any arbitrary frequency. I can only have certain possible modes of this wave on a string. And notice this, I also have nodes. I have places where the wave is not vibrating the string. So if you take a particle and you constrain it, you force it to exist. I take that particle and I constrain it to exist in a certain region of space. Its energy levels will be quantized. It can only exist in certain possible energy states, and that's because of the wave nature of the particle. So the wave nature of a particle leads to a quantization of the energy levels of particles. So you've seen pictures before of atoms where the electrons have to exist in certain orbitals. The orbital is basically a standing wave mode of an electron that's constrained to exist within an atom. And as for the wave on a string, I end up having nodes and antinodes. Fascinating. The wave nature of the particle leads to its quantization. And so if I have electrons that are existing within a certain atom, their energy levels are quantized. They can only exist in certain states. And that leads to dramatic and observable consequences, which we'll talk about in the next segment.